Let's talk about the danger zone. Ah yes, let's continue expanding our knowledge of the so-called danger zone. If you've seen my other two videos, fellatio math and section math, you may be quite familiar with this region. If not, I recommend checking those videos out first. But suffice to say, it is an area formed under a stiff curve where electronics risk being contaminated by certain fluids. In the original video, I relegated the danger zone to a simple regular integration. However, things can get quite messy in the real world of three dimensions, so I proposed a simple solution of using triangles, a very basic calculus method of integrating by slices. Anything to avoid the dreaded multiple variables. And everything will be fine if not some I mean, a valued viewer of my YouTube content made a comment suggesting I use parabolas. So, yeah. I specifically wanted to avoid using the forbidden dark arts of multiple variable calculus. This demonic magic is definitely not for the faint of heart. One might have better luck trying to solve the lament configuration. If I am called to summon the abyss for the sake of the viewers of my videos, so be it. Okay, so let's explain what we are dealing with. To measure the volume of a rectangular box, we can just multiply length, width, and height. No problem. All of us know this already. And a rectangular area is even simpler. We can also do few other shapes like circles and triangles. However, when it comes to something a little more complicated, we must get creative. Calculus is one of the main methods for finding the area of those shapes. The way it works is that we find some magic math crap that lets us determine this curvature here. As you go along this length, the right kind of crap will tell you how high this curve is at any point. Now knowing this, we can apply some calculus using this crazy thing here. When you plop this inside here, it poops out another magical blessing. This one also describes a curve based on the position on that path. The neat relationship between the two is that the value of the curve given by this guy at that point turns out to be the value of the area of this region at that same point. This point is also noted at the upper part of the integral symbol. We also have another point at the bottom that determines the start location. When you plug this value into the magical third, you get this area, which when subtracted from the larger one will give you this area. Oftentimes the bottom value will be 0, leaving us with just the big area. So this was a very basic way of explaining how all of that works. Now, when we are dealing with volume, we have to add a new dimension to the whole thing. If the shape is an even block with the same curve throughout, then we can just multiply by the new length. If, however, we are dealing with another curve, we probably will need to use multivariable calculus. We will need to figure out the crap for this curve, which will join this other crap and probably make some more crap here as well. Then this whole thing will go inside of another integral. You will then have to evaluate this thing, creating a new pile of crap. And finally solve this to get the ultimate pile of magical crap that will result in whatever volume this thing is. Now, I didn't want to deal with these cursed mathematics, but someone did suggest to use parabolas to find the danger zone. So let's do that. Just a warning, we will be using evil occult powers. But remember, I am a professional, so don't try this without adult supervision. So we take our original danger zone defined by root x. I decided that our region will be from 1 to 5. The idea then is to use the parabola to measure out the volume along this path. The illustration is the easy part. Figuring out what the damn function was supposed to be required me to summon the devil and sacrifice a virgin goat. One way to do it is to start with the parabola. You first flip it upside down, then raise it up to the desired height. Because we are now in 3 dimensions, we are using the z-axis, making our original function into root y. And we finally have the equation for this shape, which can go inside of this fun-looking double integral. The next step was to set up our limits. So this time I had to summon Cthulhu just to learn how to do all of that. Here's the quick version. You need to know the function for this boundary here. One way to do it is to set z to 0 and do a little algebra. You end up with the 4th root of y. You can now plug it into our top and bottom limit. You can use calculus magic to make the bottom into 0 by putting a 2 over here. The outer integral I already said was going to be from 1 to 5, so that's easy. And there you are, we finally set up the double integral. All we have to do now is cast a simple power rule spell for the inner part. A second power rule spell. And we're done. We have our volume. Now just to make this shape more realistic, we could include two different half paraboloids at each end. However, I will let you guys figure that one out. And for bonus marks, see if you can reverse the order of the integrals. Preparing for this video was a ridiculous learning curve for me. And this is the first double integral in my entire life that I tried to solve and actually solved. I decided to commemorate this achievement by making a painting featuring that very expression. This was definitely a challenging but fun video to make. I'm super grateful for all the subs, likes, views, and comments. I want to make a lot more content like this, so do keep them coming. And special thanks to Nathan Panning for suggesting I use parabolas. Hope you all have a great day, and thank you for watching.